is a classic integrated circuit. Here's the pinout. This is an 8-pin IC, and its behavior is like this. The output is equal to an amplifier gain multiplied by the difference of the voltage in the plus pin or in the minus the voltage in the minus pin. This value of A is around 100,000 times, so that's why it's called an amplifier. Of course, if you connect it directly like this, it has very little use except as a comparator. So it goes to the positive supply voltage in case V sub 3 is higher than V sub 2, and it goes to the negative supply voltage if V sub 2 is higher than V sub 3. But the power of this op-amp is that you can generate circuits that can do all kinds of things. You can integrate, you can differentiate signals, you can add signals, you can amplify signals, and so on. For pulse width modulation, this is the 741. So we have here the motor stage with the amplifier, the transistor, sorry, and we use 3 op-amps, and here I use the reference, and at this point I generate a triangular wave, which is compared to the value of the set value in the potentiometer. So there will be a certain time where this value will be higher than the voltage, than the triangular wave voltage, and there will be intervals of time that they will be lower. So that will generate, as using this as a comparator, will generate a pulse of different duration and a duty cycle of different duration. The frequency of the pulse width modulation is given by this resistance, or this one, which are the same, and this capacitor. Okay, and it's a very simple connection, and this here generates an integration phase, and this is an amplification phase. And as a result of this feedback here, we generate here a triangular wave. So the frequency of the pulse width modulation is given by this expression. As I told you, I generate a triangular wave using amplifiers 1 and 2, and then using the potentiometer I generate a reference. So in the final stage, in the comparator, in the amplifier number 3, when this signal is higher than this one, I generate an on pulse, and when the triangular wave is greater than this signal, then I generate a negative value, which in this case is 0. So this way I generate a pulse. Here's the circuit: the potentiometer, amplifier 1, amplifier 2, amplifier 3, and here's the transistor. Here's the capacitor C1, capacitor C2, R1, R2, R5. These are the feedback resistors here, and here's the pulse width modulation output, which I take on to the transistor, and the transistor receives the 1 pin from the motor, which is this one. Okay, and here's the setup. Here's a tachometer, power supply, DC motor with gearbox, and this is a 741 PWM circuit, and this is the oscilloscope. The experiment results with 741s is this one, and again I measure with the oscilloscope the value that I set, the duty cycle that I set by positioning the potentiometer, and then the RPMs I measure with the with the tachometer, and here's the resulting curve for several values of the duty cycle. In this case, you can see that I am able to reach 100% of the duty cycle up to down to around 28, 29%. And you can see again that below this values, either the motor stops or I am not able to reach the pulse width modulation because the circuit doesn't allow it. So this is sort of the limit, the lower boundary with this 741 circuit. And you can see also that it's not linear. It's not a straight line. Okay, thank you very much, and I hope that's been useful for you.